In this lecture video, we'll be understanding a numerical based on root locus. Draw the root locus diagram for a transfer function given by g of s into h of s equals k divided by s into s plus 5 into s plus 10. So this is the equation which has been given. The first step is finding poles and zeros. The denominator of the given transfer function always signifies the poles and the numerator signifies the zeros. So from the given equation, the equation which is given to us is k divided by s into s plus 5 into s plus 10. So this is the equation which is given to us. The denominator s term signifies poles and the numerator s term signifies zeros. So if we observe there are three s terms out here, so there will be three poles. So the number of poles p will be equal to 3. That is, s will be equal to 0. That is the first value of pole. S plus 5 equals 0. We have to equate that to 0. So when s plus 5 equals 0, s will be equal to minus 5. So that is the value of second pole. S plus 10 equals 0. So when s plus 10 equals 0, the value of third pole will be equal to minus 10. The same thing is being written over here. So there are three poles over here having the values 0, minus 5 and 10. If we observe, there are no s terms in the numerator of the given equation. So because there are no s terms in the numerator of the given equation, there are no zeros. So after finding poles and zeros, we have to plot these poles and zeros on our plot, root locus plot. Along x-axis, we'll consider real axis, which is given by the symbol sigma. Along y-axis, we'll be considering imaginary axis, which is normally signified as j omega. Normally, poles are represented by cross marks and zeros are represented by zeros. But here, we have represented poles as circles, blue circle, and we have represented zero as a red triangle. In this particular problem, we have no zeros. Hence, there are no red triangles over here. So the value of three poles are s is equal to 0, s equals minus 5, and s equals minus 10. So these are the three values of poles which we have got, which has been plotted. So to find the root locus here, how the root locus has to be plotted, we place a test point somewhere over here. So if I place a test point towards the right hand side of this test point, we have one pole, which is odd number. So whenever there are odd number of poles and zeros, only then root locus exists. If there are even number of poles and zeros, then root locus will not exist. For example, if we have one pole and we don't have any zero there, that means number of pole is 1 and number of zeros is 0 towards the right hand side of the test point which we have considered. So the summation of this pole and 0 is 1, which is odd number, hence root locus will exist. In the same case, if I consider if we have one pole and we have 1 0 in our test case, if we have one pole right hand side to our test case test point which we have considered, if we have one pole and 1 0, 1 plus 1 is 2. So if there are even number of poles and zeros, root locus will not exist there. So the same thing is being shown out here. We take a test point over here towards right hand side of this test point. If we observe there is only one pole, hence root locus exists here. Root locus exists up till this particular point, because up till this particular point, if we see towards the right hand side of this test point which we are considering, there is a odd number of poles, means odd number of poles and zeros. Only one pole is there, which is odd number, hence root locus will definitely exist. So up till here, root locus will definitely exist. Next, let me place a test point over here. So if we observe towards the right hand side of our test point, we have two poles, one pole and second pole. So because we have two poles, it forms even number of poles. So when we have even number of poles, root locus will not exist there. Similarly, if I place a test point over here, again right hand side to that, if we observe, we have two poles, hence we will not be having any root locus here. Similarly, let me place a test point over here after minus 10. So right hand side to this test point, if we observe, we have 3 poles, 1, 2, and 3. So because there are 3 poles and 3 are is an even number, definitely there will be a root locus. So this particular pole, always the root locus starts from pole and it will end at either 0 or it will end at infinity. Because there are no zeros over here, all these poles, root locus should start at pole and it should end at infinity. So with respect to this particular pole, the last pole which we have, which is present at -10, it starts at pole, root locus starts at pole and it ends at infinity. It is done. So root locus for this particular pole is done. Whereas we also have root locus over here, but there is no path for this root locus to end at infinity, because this particular root locus cannot be extended up till this infinity because there is no path over here. Hence, we have to find another way such that these poles reach infinity. Step 3 is finding angle of asymptotes and centroid. So we already know that from our problem, number of poles is 3 and number of 0 is 0. So to find angle of asymptote, we'll be using a formula 2q plus 1 into 180 divided by p minus z, where p is the number of poles, z is number of zeros. To find this value of q, we already know what is p. P is 3 and z is 0, but we don't know what is the value of q. To find q, we will be using the formula q is equal to number of poles minus number of zeros minus 1. So q value will be equal to number of poles in our problem is 3, number of zeros is 0, and minus 1. So 3 minus 1 is 2. So q value is equal to 2. That means the q value which we have to write should be 0, 1, 2. 0, 1, and 2. These three are the values of q which has to be substituted. So for q value is equal to 0, angle will be equal to, in this particular formula, for q value equals 0, we'll substitute this q is equal to 0 in this formula. We'll get 2 into 0 is 0, 1, 0 plus 1 is 1. So 1 into 180 is 180 divided by p minus z. Number of poles is 3, number of zeros is 0. So 180 divided by 3 will give us 60 degrees. Similarly, let us substitute for q is equal to 1. So when q is equal to 1, 2 into 1 is 2, 2 plus 1 is 3. So 3 into 180 divided by p minus z. 3 minus 0 is 3. This 3 and this 3 gets cancelled. So the value which we get is 180 degrees. So this is angle of asymptote 2. Similarly, when q value is equal to 2, substitute q is equal to 2 over here. So 4 plus 1 will be equal to 5. 5 into 180 divided by number of poles minus zeros is 3. The 3 minus 0, which is 3. So when we substitute or when we solve, we'll get the value as 300 degrees. So that is angle of asymptote 3. So now we have found out angle of asymptotes, and why we are finding out this angle of asymptotes and centroids is such that to make sure that the poles reaches infinity. Where we have to plot this angle of asymptote? That is the next question. So this angle of asymptotes will be plotted by means of centroid. Again, to find centroid, we'll be using this formula. Centroid is given by summation of poles minus summation of zeros divided by p minus z. So the value of poles which we have in our equation is 0, minus 5, and minus 10. So summation of those poles is 0, plus of minus 5 is minus 5, plus of minus 10 is minus 10. So 0, minus 5, minus 10. We don't have any zeros. So 0 is equal to 0, whole divided by 3. Minus 5 minus 10 is minus 15, divided by 3 gives us minus 5. That means the centroid is minus 5. So using this centroid as minus 5, we'll be plotting centroid on the real axis, and using that we will be plotting angle of asymptotes. So thus the centroid of the root locus is at minus 5 on the real axis, somewhere over here. So using that centroid, so we'll place a protractor and we'll mark 3 angles. 60-degree angle, which gives us angle of asymptote 1, 180-degree angle, which gives us angle of asymptote 2, 300-degree angle, which gives us angle of asymptote 3. we have found out centroid as -5, and based on that centroid, we have drawn three angles: phi a1, phi a2, and phi a3. Next, this root locus from this particular pole has already reached infinity, but the root locus from these two poles has not reached infinity. We have to find a way such that the root locus from these two poles reaches infinity. For that, we have to find breakaway point. Always the root locus starts from poles and it ends at infinity. The root locus starts from poles and it ends at infinity, or it will end at open loop 0. Root locus will always start from poles and it will end at 0, or it will end at infinity. Here, the root locus will start from these two poles, and we have to make sure that we get a point such that from that particular point, the root locus will reach infinity. That point is called as breakaway point. So if we observe for this particular pole, the root locus has started from pole, and it has, because there are no zeros, it has the root locus has reached infinity because there's a perfect root locus path over here. But even here we have a root locus path, but the root locus cannot reach infinity because it doesn't have a valid path here. Always the root locus will start from pole. So the root locus will start from these two poles. It should meet at a point. That point is called as breakaway point. From that breakaway point, it should reach to plus infinity and minus infinity. So next important thing which we have to do is we have to find breakaway point. So to find breakaway point, we'll be using this equation: 1 plus g of s into h of s equals 0. So we already have g of s into h of s in our problem. So 1 plus k divided by s into s plus 5 into s plus 10 equals 0. So when we simplify that, take LCM, s into s plus 5 into s plus 10 plus k equals 0. Yes, when we multiply this s plus 5 and s plus 10, we get s squared plus 15s plus 50. And when we multiply this s into this term, s cube plus 15s squared plus 50s plus k equals 0. Or k equals, when we send this entire term towards the right hand side, it becomes minus s cube minus 15s square minus 50s. Next, we have to differentiate with respect to s. So dk by ds will be equal to minus 3s cube 3s square minus 30s minus 50. Let us take minus as common, will get us minus 3s square plus 30s plus 50 equals 0. If we send this minus towards the right hand side, it becomes we'll be sending this minus towards the right hand side. So we'll arrive at this equation: 3s square plus 30s plus 50 equals 0. Let us divide this by 3 such that we get just the square term without this coefficient 3. So s square plus 30 by 3 is 10s plus 50 by 3 is 16.67 equals 0. Now, the roots of this equation when we solve in calculator will be getting as minus 2.113 and minus 7.88. So these two are eligible breakaway points. But in these two, we have to choose one breakaway point. So we already know, if we clearly observe in this particular scenario, in the root locus diagram, whatever we have got, so the breakaway point should be between 0 and minus 5 only. It should not be after minus 5 because we don't have any path over here. So from that, we can easily conclude that the breakaway point is minus 2.113. But we have to prove that. So let's verify that by putting the value of the root, whatever we have got in the equation, k equals minus s cube minus 15s square minus 50s. So when we substitute this s value as minus 2.113 in the above equation, we will get the value as 48.112, which is a positive value. So the value of k is found to be positive, and hence this s value, whatever we have considered, which is minus 2.113, can be considered as breakaway point. It is a valid breakaway point. Similarly, let us verify this minus 7.88. We already know that it cannot be taken as valid breakaway point, but let us prove that. Let us consider s is equal to minus 7.88, and let us place this s value in this k equation. So when we substitute that, we'll be getting a negative value. So because the k value is found to be negative, this s value, which is minus 7.88, cannot be taken as valid breakaway point. So now we have found out breakaway point, which is minus 2.113. Next important step is finding intersection with imaginary axis. Here, we will find the intersection points of the root locus on the imaginary axis using RH criteria. So we already know the equation which we have got here, which is s cube plus 15s square plus 50s plus k equals 0. That is the equation which we have got, characteristic equation. So that characteristic equation will be taken and we'll be using RH criteria. The highest power of s is 3. So s cube, s square, s to the power of 1, s to the power of 0. The coefficient of the characteristic equation will be placed in the first two rows of root array, 1, 15, 50, k. So the value for s to the power of 1 row will be 15 into 50 minus 1 into k divided by 15, which gives us 750 minus k divided by 15. The next value will be 0. Next, the value for this s to the power of 0 will be 750 minus k divided by 15 into k minus 15 into 0 is 0 divided by 750 minus k divided by 15 will give us k. The next value is 0. Now, from the third row of s, this row of s, we have got equation as 750 minus k divided by 15 equals 0. Let us equate it to 0. So when this 15 goes to the right hand side, 15 multiplied by 0 is 0. Hence we get 750 minus k equals 0. So when we send this 750 towards the right hand side, k value becomes equal to 750. From the second row, we can form the auxiliary equation. So when we are forming the auxiliary equation, a of s will be equal to, from the second row, just beside this 15, the sv which we have is s square. So 15 s square plus the next value is k into s to the power of 0. We have to consider alternate powers of s. S to the power of 0 is anyhow equal to 1. So k into 1 is k. So the auxiliary equation will be equal to 15s square plus 1. 15s square plus k. So the same thing is written out here. 15s square plus k equals 0. That is the auxiliary equation. Whatever value of k which we have got previously, let us substitute that over here. So when we put that value over here, we'll get 15s square plus 750 equals 0. Or 15s square is equal to minus 750. S square is equal to minus 750 divided by 15. S square is equal to minus 50. So S value will be equal to plus or minus 7.071 J. We'll be getting two values of S because we have S square term over here. J 7.071, it is one of the value. Second value is minus J 7.071. Both of these points lies on imaginary axis. So this is the intersection point of root locus with respect to imaginary axis. So previously we have found out the breakaway point. So from the breakaway point, the root locus will travel and it will cross the imaginary axis at 7.071 and minus 7.071 J. Step 6, to find angle of departure. Because there are no complex poles in our given transfer function, there is no need to find angle of departure in this particular problem. But if we have complex poles, there is a necessity for us to find out angle of departure. But in our problem, it is not there. Similarly, if we have complex zeros, even there we have to find out angle of arrival, which is not there in this particular problem. So in our problem, because there are no complex poles or complex zeros, we don't need to find angle of departure and angle of arrival. Finally, the root locus looks somewhat similar to this. If we observe from the centroid, we have drawn three angle of asymptotes, 60 degrees, 180 degrees, and 300 degrees. And later, we have found out the breakaway point over here. The breakaway point is having the value minus 2.113. Always the root locus travel from poles to 0 or poles to infinity. So here from this particular pole, it is traveling, root locus is traveling to infinity. That is done. From these two poles, we have found out the breakaway point is minus 2.13. So from these two poles, the root locus will travel up till the point minus 2.113, and from this point or to minus 2.113 on the real axis, the breakaway point, which is called as breakaway point, the root locus touches over here from both the poles, and it will cut the imaginary axis at plus 7.071 and minus 7.071 j, and it reaches infinity. Always the root locus, we have to remember this point, always the root locus will start from pole and will end at 0, or it will end at infinity. If zeros are not present, it will end at infinity. This particular pole, the root locus has started at pole and it has ended at infinity. For these two poles, the root locus has started moving away from the pole. At the breakaway point, it will meet, and from there, it will cross plus 7.071 j on the imaginary axis and minus 7.071 j in our imaginary axis, and it will start moving to infinity. And always this particular root locus, whatever we have drawn, which is with respect to the intersection of this imaginary axis, should be traveling in parallel with the angle of asymptotes which we have considered. If we observe this root locus which we have considered over here is moving in parallel with phi a1, and this root locus which we have considered over here, the negative imaginary axis, it is moving in parallel with the third angle of asymptote. So this is how we draw the root locus. I hope that you have understood this video lecture. Thank you.